All right, my forecast for exam 3, I know that chapter 21 will be on it. I know that chapter 22 will be on it. And I know that polymer chemistry will be on it. It's possible we'll do some other stuff, but there won't be a lot more than that. So as you start to read ahead, I would go ahead and just kind of look at chapter 21 right now. The acid-base chemistry we're going to do is in chapter 3. I'll supply you guys a pKa table. You know, I always get asked, like, what pKas do we have to know? That's a good question. I will try to supply that. All right, so let's just do this. All right, do that acid-base problem. So, well, when I say do it, look at the sheet you have, work all of that stuff. So a mechanism, draw me the products, draw me the mechanism, estimate the pKa of the acid on both sides, and tell me which direction the equilibrium is. They're extras of the synthesis problem. All right, I'm gonna go ahead and jump into this. I see some folks are still writing. So I've written here, you guys should have learned this in chapter 3, maybe Gen Chem, high school chem, this ARIO thing. So if you're trying to judge an acid-base reaction, really what you're trying to do is judge the stability of a lone pair of electrons. Maybe sometimes a bonding pair of electrons. All right. And in general, a lone pair, excess charge, excess electrons would rather be on the more electronegative atom. They would rather be delocalized. They would rather be within inductive reach of electronegative atoms. And then they would rather be in an orbital closer to the nucleus, right? The nucleus is positively charged, so electrons would like to get toward the nucleus. It's really important to remember this is just a guide. Okay, E equals mc squared. That we haven't found anywhere that doesn't exist. This, lots of violations of this. And some of that's memory, and that obviously comes easier if you work in chemistry, right? So I go to the lab every day for 10 years and I mix chemicals and I sort of get an idea of this is a strong acid, this is a strong base. You also having a pKa guide helps you with that. So like I said, I'm going to give you guys a pKa table that I expect you to know. I'm not asking you to memorize these pKas just because I want you to memorize pKas. Right? A stronger acid has a lower pKa. So if you have functional groups and proton types kind of grouped by pKa, even if you don't know the exact one, you just know this pKa is lower than that one, you can figure out which way the equilibrium is going to be going. All right. So in this case, like I said, you got to figure out which hydrogen is going to be the acidic hydrogen. And I don't want to make too much of this, but right, like this, there's a functional group in this set of molecules. That's a carboxylic acid. Again, I make this joke a lot. The word acid appears in the functional group. There's a good bet it's going to be the acidic proton. That is not 100% thing, right? We saw examples in chapter 20 in the Fischer esterification where the carboxylic acid is protonated and it's protonated on the oxygen. But it's only going to be protonated by a really strong acid. And again, from Gen Chem, you should know the really strong acids. Principally in this class, HCl, right? HBr and HI also fit in there. Sulfuric acid, phosphoric acid, nitric acid, those are the sort of mineral acids. There are some stronger acids that we know. Industrially, you'll find Lewis acids that are much stronger than those. But like in a normal lab, sulfuric acid is going to be about the strongest acid we see. Okay, so if this is the acid, we decide that this is the acidic proton. It's going to be the case this time. Then we have to figure out what the basic atom is, right? Either the basic atom or the basic bond. So again, a bonding pair of electrons can be the base. And you guys saw this back in Orgo 1, right? If you protonate an alkene, so the pi bonding electrons are the pi bonding electrons are the base. All right, so we've got two molecules over here that can supply a lone pair of electrons. I just said you can have a bonding pair be the base. Sigma bonds usually aren't going to do that, right? The sigma bonding pair, those are low energy stable bonds. So we have to decide between the lone pair on this nitrogen and the lone pair on that nitrogen. And here's where you should use analogy. So when we talked about carboxylic acid derivatives, where did I say to always protonate? Say that. Well, but yeah, but like which O gets the proton? That one. All right. Yeah, I said to protonate this oxygen, right? And that's resonance. Basically, this oxygen is kicking electron density upward. This oxygen, this should look very much the same. And so this nitrogen is going to take the proton the lone pair goes from the, or sorry, the arrow goes from the lone pair on the nitrogen to the H. That makes a nitrogen-hydrogen bond. And then the second arrow goes from the bonding pair between the O and the H to the oxygen. And then I said this, you know, leading up to the exam, if you draw those arrows, draw the result of what comes out of those arrows. So an NH bond and then an O with an extra lone pair. So that's going to give us I'm going to leave off the extra hydrogens now. Maybe not. I'm going to put those on. And again, now we get resonance stabilization of both of those. So we can get a resonance, we get resonance delocalization. Here. And we get resonance delocalization over here. Right, so the resonance delocalization explains why the nitrogen with double bond gets protonated and not the nitrogen with the single bond. If you protonate the nitrogen with a single bond, that charge is localized on the nitrogen. It can't be delocalized. Moreover, you would wind up with a positive end, right? If that end, let me draw that. And so if we protonate the nitrogen here, we have a positive end sitting next to a partial positive C. That's unstable. And there's no way to delocalize electrons to stabilize this nitrogen, the positive charge in this nitrogen. That nitrogen has 8 electrons already, so it's got a full octet. They're all sigma bonds. So you can't just, like, a lot of times people will, especially on an exam under duress, they'll be like, oh, we'll just stabilize that charge here. Or we'll take this lone pair and we'll just push it down, like pi bond, pi bond. You're going to make that carbon have more bonds than it should. And that nitrogen can't have more than 8 electrons, right? My whole thing about carbon can't have more than 4 bonds. That's the octet rule. A bond is 2 electrons. Carbon can't have more than 8 electrons. No atom can have more than 8 electrons. I sure heard. All right. No atom can have more than 8 electrons. No second row atom can have more than 8 electrons. Okay, so don't draw it this way. Anytime you've got carbon, some atom, pi bond, single with that carbon single bonded to a heteroatom, the proton always goes on the double bonded atom. All right. So now, and if you want to think about it, we're almost thinking about that lone pair, right? The lone pair goes from, the lone pair we're talking about goes from the nitrogen, being localized on the nitrogen, to being delocalized on the oxygens. You guys probably can't see that color out there. And if you think about it that way, you'll come up with the direction this equilibrium lies. What direction do you think it lies? Lies to the right. All right. So a lot of ways to say this. Big fat arrow like that. You can write the word favored. You can write a sentence where you say the equilibrium lies to the right. Whatever. I will interpret it. If you say the equilibrium favors products, I would probably interpret it that way. But remember, this is an equilibrium. These molecules don't know if they're on the left or the right. They don't know if they're products or reactants. If you mix them up, they'll go both ways. All right, so yeah, so the right side is favored. Give you 30 seconds for this. You might already have it. Identify the acid on both sides. All right. So we've already done it over here. On the left side of this equation is written the carboxylic acid is the acid, it's the proton donor. On the right, then once you decide that, it all works out, right? The conjugate base of the acid is going to be the base. We'll call it the conjugate base. Again, it doesn't know it's a conjugate base, it just knows it's a base. So acetate has a negative charge. In solution, it's going to act as a base. And that's going to make, so then this is going to be the base. The conjugate acid of the base is an acid. Right? So if we're looking at acidic protons, well, it could be either one of those two, right? We've now got two identical NHs up there. So either one of those could get taken. So now you should be able to come up with a pKa for the two acids. Bases don't have pKa's. The only thing that has a pKa are the acids. Anybody recall the pKa of carboxylic acids? 3 and 5. I thought you were actually telling me 5. That's like,
Oh,
no, I was like, yeah, 5 is great. You remember it? 3. It's hard. All right. pKa for acetic acid is actually like 4.7. 4.7 is needlessly detailed. You really only need to remember that it's between 3 and 5. What does that make the pKa of the conjugate acid? It's above 5. If you have 6, if you're accurate in saying that the right is favored, the pKa of the acid on the side that's favored has to be higher than the pKa of the acid on the side that's not favored. All right, the higher number pKa is favored. This is why knowing pKa is really useful, not for solving exam problems, but if I dump a whole bunch of chemicals together, some of them are acids, some of them are bases, I can work out where the equilibrium will lie. Right? I want to maximize the concentration of the weaker acids. This also means in terms of the bases, right? The stronger base lies on the same side as the stronger acid. I'm going to get rid of ARIO. So the stronger acid is over here, also the stronger base. This makes some people a little confused because, right, if you look on the left, everything's neutral. On the right, the side I'm saying is favored, molecules are charged. Charges aren't bad. A lot of times you're going to see charges that are favored. Okay, so does anybody recognize that functional group? Sorry. No, you guys, I mean, we haven't covered it in this class. Why would I ask you guys a question we've already covered? That's easy.
An enemy?
It's not an enemy. That is an amidine. You don't have to know that. So the folks saying imine, if you remember, a carbon-nitrogen double bond is an imine. A nitrogen bonded to a carbonyl is an amide. So amidine. It is part. There's another functional group where this is a nitrogen. You guys might have seen. Anybody here had cell bio? Did you guys have to memorize amino acids? We're just slacking. It's fine. So at some point, you guys are probably going to have to memorize amino acids. I used to do it. So I used to do it in Orgo 2. Then I was told, no, they do that in cell bio. You don't have to do that. Cool. So according to you, then I should make you guys memorize it. So I'm not going to do that. All right. So I am not going to make you memorize the 20 proteinaceous amino acids. Some of you need to know it. Some of you probably don't. I think if you take the MCAT, you really ought to know. So before you take the MCAT, DAT, whatever the one for vets is, probably not on the LSAT. I don't know. Could be. Who knows what they do? You should memorize the side chain, right? So we're gonna talk about. We've talked about carboxylic acids. Chapter 22 is amines. So what am I trying to draw? It's so many bucks. That is an alpha amino acid. Can you guys see that at home? Yeah. That is the alpha amino acid glycine. All right. So if any of you drink like, protein, the snake oil that we're selling these days, where you like dump granules of brown stuff into a drink and then drink it and you get big. Like seriously, you can just eat almonds. It does the same thing. Anyway, you'll probably see in the ingredients, glycine, asparagine, all these amino acids that are in there. So the alpha amino acids are carboxylic acids that have a nitrogen or an amine bonded to the alpha position. So this is sort of older terminology, right? So the alpha position we'll have alpha positions in many different kinds of molecules. If you go back to elimination, chapter 7, yeah, I think chapter 7, right? We do E2 elimination. You have to have a beta, you have to have a proton beta to a leaving group. The leaving group is bonded to the alpha carbon. In carbonyl chemistry, we call the alpha position the carbon bonded to the carbonyl, not the carbonyl itself. So, and that's chapter 21. We're going to talk about reactions at the alpha carbon of carbonyl compounds, right? If you put an amino group there, you get alpha amino acids, and that's what makes up like 99% of the residues in our proteins. And when I say our, I mean earthlings, whether you're human or a cockroach or a plant or an amoeba, the proteins that make you up are mostly alpha amino acids. This is not how glycine appears if you dissolve it in water. I want you guys to draw how glycine appears if you dissolve it in pH 7 water, neutral water. All right, I forgot to, as I often do, I forget to finish thoughts. It's not just in here, right? I actually do this in real life too. I'll walk into the kitchen, I'll say 2 sentences to my wife. Third sentence contains a really pertinent, important information, and I'll just walk out without that. So, okay, she knows me well. She knows what that third sentence is going to be. pK of this acid is like 13 or so. All right, it's actually a very weak acid. The amidine base, right? So a trivalent nitrogen single bonded to a carbon nitrogen double bond. That's actually a really strong base. So just an amine by itself is a pretty strong base. All right, so kick in a little more resonance electron density on that nitrogen, it becomes an even stronger base. If you put a nitrogen, if you put a nitrogen there, you get the guanidine functional group. That is on the side chain of an amino acid called arginine. I have not taken cell bio. And that you'll find that is always protonated under physiological conditions, and it is often used as like a really strong base in biochemical reactions. Okay, and it's basically the strongest base you're going to see floating around proteins. So glycine, we've got a basic nitrogen here, we've got a carboxylic acid. Again, usually if I dissolve glycine, if I take my protein drink, I dump it into water, like I've got a bunch of glycine molecules. And so what this is going to look like in water H. So that in blue is how glycine appears, or is the structure of glycine in water, neutral water. So again, pKa here, glycine is going to be like 4. pKa of this amino group is going to be like 11. So this gives you, this is basically the result of the Henderson-Hasselbalch equation. I'm just going to put it up as if we didn't solve that. Right? Sorry. Might scratch that on the timer. All right, if the pH is lower than the pKa, the protonated form is going to predominate. All right, so again, at pH 7, for the amine, the pKa is 11. So the pH is lower than the pKa. And that means the acid form, the protonated form, is going to predominate, right? If the pH is if the pH is more acidic than the pKa, you're going to have protons on that atom. Flip side. Right? If the pH is greater than the pKa, the basic form or the deprotonated molecule will exist, right? So if you look at the carboxylic acid, pKa of 4, if the pH is 7, that's higher than the pKa, and so the carboxylate is going to be deprotonated. All right, again, this falls out of the Henderson-Hasselbalch equation. Memorizing this is well worth doing. You're going to work in any kind of biochemical setting. So usually that's going to be buffered, right? Our blood is buffered. The inside of cells is buffered. When we do biochemical reactions in the lab, we usually use buffer. So we know what the pH is. So physiological pH, all of us in here right now, our blood is right around 7.4, pH 7.4. Right? If it's 7.45, you got problems. If it's 7.35, you have a problem. So we vary a little bit, like 7.38, 7.42. You're not going much farther than that. So again, amino acids at pH 7.4, the amino group is going to be protonated because our blood is buffered to be more acidic than the pKa of the protonated form of the amine. Likewise, carboxylic acids with a pKa of around 4, like I said, 3 to 5. 3 to 5 is all lower than 7.4. So they're going to be deprotonated. Make sense? What happens if the pH equals the pKa? There is a mixture. What kind of mixture? No, not racemic. But no, I'm not. So it's not stereochemistry. But what is a racemic mixture? 50-50. It is a 50-50 mix. So that's actually how we get pKa. The pKa is defined as the pH where an equal amount of protonated and deprotonated form of the acid exists. All right. There's always a mixture. This is important. All right. As the pH gets closer to the pKa, right, you have more of the minor form. So, right, the ammonium has a pKa of 11. At pH 1, you have 1 deprotonated amine for every 10 to the 10th ammonium. Like that's nothing. At pH 9, you have 1 deprotonated amine for every 99 protonated amines. Right. So it's again, pH is logarithmic, so orders of magnitude. At pH 10, right, 10% of those amine groups would be deprotonated. Make sense? All right. So yeah, I'm not going to write it down because I can't bend down that far. If the pH equals the pKa, you have a 50-50 mix of protonated and deprotonated forms. Again, that's the definition of pKa. It is really useful, like in thinking about biochemical stuff. All right, I have put up on the third panel another acid-base equilibrium. I'm going to ask you guys to spend some time thinking about that. This will launch us into chapter 20. You guys might get some handy on this. We're already the only people on the street that do temperature. Just specify my wife's the only person on the street. It really is. Everybody else around is hired. I'm going to put something else on here. I am recording this, I guess. All right. That O minus is almost always going to have, well, almost. That O minus is always going to have a counter ion. That counter ion is never H plus. Hydrogens make covalent bonds. But it could be lithium or potassium or sodium or rubidium or tungsten. It could be it could be pretty much any other metal cation up there. And you might, so this would normally be written with a OCH3, right? That looks neutral, but if you see sodium in a compound, it is +1. If you see lithium in a compound, it's +1. Potassium, same thing. So that means the rest of the molecule has, if I have not shown charge, the rest of the molecule has to be minus. And then you got to figure out where the minus goes. And I think everybody's up on that right now. I know I'm repeating things, but right, if OCH3 is minus, it's not going to be the H is. Could be the C, but it's not going to. It's going to be more electronegative thing, right? It's going to be that oxygen. Okay. So let's do the mechanism. Well, first of all, what's the acidic proton? Nobody's confident about this. How many people think the acidic proton is this? Be honest. You're not honest on Halloween. All right, good. It is not that one. That one gets, so the reason probably some of you, like, I know at least 5 or 6 people came to me before the exam. We're like, I think this is an acidic proton. And it looks like it ought to be. I thought it was for, a long time. Like this was, I've told some people, like I was initially quite good at organic chemistry. This will hopefully not surprise you. Like, I liked the class, I did well in the class, like I answered things correctly. Like there were definitely classes where I was not that. And so I'm not trying to show off, right? Like, but I grew up to be a professional organic chemist. It's not weird. But this went through me. There were a couple of little features of organic chemistry that really threw me. And aldehyde protons not being acidic really threw me because it's bonded to this carbonyl. Carbonyl electron withdrawing. If you come over here and look, right, the carboxylic acids are acidic because the carbonyl's electron withdrawing. They're withdrawing electrons from this atom, right, which is going to stabilize the negative charge there and weaken the bonds that atom forms. This H, anybody know the chemical shift of this proton? What does it?
No, I should.
Yeah, you should. Chemical shift of this proton is like 9 to 10. And it's way downfield. It's way on the left. If you look at a full proton NMR, way down on the left. And that's because the carbonyl is electron withdrawing. So the carbonyl is actually withdrawing electron density from this H quite a bit. But that's not weakening this bond. It's pulling, it just means that this bond is very polar, right? The H still is going to maintain that. So the pKa of this thing is like 35 or something. It's more acidic than it would be if it were an alkane, but it's not like notably acidic. So that's going to leave these 3 protons. Okay, so this H is acidic because of the electron withdrawing nature of the carbonyl, right? So the carbonyl is withdrawing electron density from the O. That makes that OH more acidic than it would be if it were, or not neutral, but not bonded to a carbonyl. So you guys know this, right? Alcohols are less acidic than carboxylic acids. The pKa of an alcohol is like 15 to 7. pKa of a carboxylic acid is 3 to 5. So the carboxylic acid is a lot more acidic than you would think it would be just by being an OH. You have the same, the carbonyl atom H. You have the same thing going on here. So that any of those 3 H's, and they're all equivalent. Those 3 methyl H's are all equivalent. Those are all more acidic than you would expect them to be. How about the acidity of these 3 H's? The 3 H's on the methyl on that side. They're bonded to oxygen. Or sorry, they're bonded to a carbon, but the carbon's bonded to an oxygen. But there's no, if we pull the H off of that carbon, we get a C minus. We get a C minus next to an O minus. Like carbon minus is already going to be pretty crappy if it's not delocalized. Being next to an already negative atom is going to make it worse. So these are not particularly acidic. So our mechanism is going to go from the basic atom. We've got 2 basic atoms, if you want to look at it that way. Right? How do I figure out the basic atom? A basic atom is a good electron donor. Right? It's able to donate electrons. We've got 2 potential, like none of the H's have electrons. The carbons could donate sigma electrons. Again, sigma electrons are stable. That's why, they're bonds. They don't break unless we do something to them. So really, we've got 2 different basic atoms. It could be the oxygen on the carbonyl. Go back to chapter 20. Lots of examples of carbonyl oxygens being protonated. We usually protonate them with sulfuric acid. something strong, some really strong acids. Well, those CHs on the other side are not strong acids. We've also got an O minus, 3 lone pairs. I'm trying to get at this, like, you guys probably at this point recognize methoxide as being a strong base. So that is a relatively strong base. It looks like hydroxide, which should be your sort of go-to, that's a base, right? If you don't know at this point hydroxide's a base, learn it. The other way to think about this, though, if the atom is the same, right? So we've got our choice. The basic atom is going to be oxygen. Either way we go. The oxygen with the greater electron density should be the stronger base. Okay, so a negatively charged oxygen versus a neutral oxygen. The negatively charged oxygen has more electrons to donate. So this is going to be our basic atom. These H's are going to be our acidic atom. So I'm going to just use the closest one here. So draw what you get with those 2 arrows. If you don't already have that, I'll give you like 45 seconds. If you don't already have that drawn, draw it. All right. I've drawn my answer. Does it look like your answer? There is a problem.
Which was again the negative charge.
I'm forgetting a negative charge. There's a lot of different ways to think about forgetting the negative charge. But one thing you should look at, I didn't draw the sodium over here, right? If I draw the sodium over there, well, let me back up. The charges have to balance left and right. All right, in an acid-base reaction, that's not a redox reaction, the charges have to balance. So we have, it's either neutral, if we count the sodium, it's neutral over here. I guess I've drawn it, you could fake yourself out. I'm gonna actually get rid of the sodium. That's not necessary. Just that out of existence, sorry. We have a negative charge on the left, neutral on the right. That cannot happen. So the negative, and then the other way is just look at this carbon, right? A carbon that doesn't have 4 bonds is going to have a charge or a single electron. Okay. 3 bonds and a lone pair is negative. 3 bonds, no lone pair is positive. 3 bonds and 1 electron is neutral. 3 and a lone pair, this is negative. And again, you don't have to necessarily draw the lone pair. You're certainly welcome to. But you could have just shown that as a negative. If you show the negative charge, I'll know that you mean there's a lone pair. It helps you to think about where things are by drawing lone pairs. Draw the lone pair. Draw a resonance structure of the negative carbon. Good. Sorry, I forget you're taking notes on that. I was like, you haven't written anything. You've not written anything. Consider what the pKa of methanol is while you finish the resonance structure. All right. So the resonance structure here, we can move the pi electrons there to make, or sorry, we can move the lone pair to make a pi bond. Pi electrons up on the oxygen. That's our resonance structure, right? Over here, if we come back to the carboxylate, right? If I have a carboxylate ion, I can delocalize that charge onto the other oxygen as well. Exactly, it's the anion that we're working with right now that has a negative carbon in one resonance structure is exactly analogous to the carboxylate. All right, so the carbonyl is making these CH bonds weaker, more polarized, more acidic. And then the negative charge that results by pulling one of these H's off is delocalized by resonance onto the oxygen. So which of these two resonance forms looks most stable? Which one do you expect to contribute more? The bottom, right? So the way we judge that, in both structures, every atom has a full octet. So that's usually the first thing to look at. Is there, like with a carbocation next to an oxygen, right? A carbocation doesn't have a full octet. So if you can donate electrons to it, move the positive somewhere else so that everything has a full octet, that's going to be the best thing to do. Here though, every atom's got a full octet no matter what. So negative on the carbon, negative on the oxygen. The excess electrons on the more electronegative atom makes that more stable. So structurally, if we could take a picture of this molecule somehow, it would look like the bottom. In terms of reactivity, this carbon is going to be nucleophilic in basic. Right? We can absolutely use that carbon as a nucleophile. This is called, these together are called enolates. Right, so again, carboxylic acid, carboxylate. So if you take the name of the carboxylic acid and then you pull the proton off, ic acid turns into 18. So like benzoate is the conjugate base of benzoic acid. This is an enolate. We actually have, and I'm going to go into this more on Wednesday. We have an enol. All right, the enol is a carbon-carbon double bond bonded to an OH. The enol, generally speaking, greatly favors the keto form. All right, so if you have a ketone that's got an alpha proton at equilibrium in water, you're going to have like 1/10 millionth of a percent enol. Again, we'll go into that on Wednesday. Okay, pKa of methanol, roundabout. It is higher. Yeah. Yeah, it's really close to water. So what is the pH of water? 7. It is not 7. 15.7. Neutral water. No. This is a good. I'm glad we went here. Not where I intended to go. What's the pH of neutral water? 7. There you go. pH in neutral water is 7. That's where we have an equal amount of H3O plus and H2O. And the concentration of both is like -7. The pKa of water is 15.7. So the first of this is mixing up H3O plus. So we're looking at it, not H3O plus and water. Right? Good, I said that before. The pH 7 is where we have an equal concentration of H3O plus and hydroxide. Right. H3O plus is not the conjugate acid of hydroxide. Hydroxide is not the conjugate base of H3O plus. Water is between them for both. So 15.7 is where we would have an equal concentration of water and hydroxide. pH like 0 is where we'd have an equal concentration of H0 plus and water. So it winds up, we sort of hammer out in the middle somewhere, pH 7 for neutral water. So the pKa of water is 15.7. Methanol is like 16, I think. Alcohols in general. (15 to 18), not even 15. Well, yeah. So the reason, and I had some questions about R groups. This is probably a good time, the class after an exam. Right? This is the first class after the exam, right? Exam feels like it was 20 years ago. No? Fresh in your memory? Sorry. For me, I told somebody this morning, I had a busier than average social week. All right. It may surprise you. I don't have like a super active social. I also have a lot of work going on. So I actually worked like almost full day, Saturday and Sunday, and then coupled that with like seeing people. Anyway, weird weekend. R groups. I remember talking to some of you about what does R mean in a molecule, right? So R here in an alcohol. So R is not H, and here R is definitely not H, because if R was H, that'd be water. Water is not an alcohol, but water behaves like alcohols, or rather, alcohols behave like water a lot of times. R here is not a carbonyl. If it was a carbonyl, you'd have a carboxylic acid. It's also not a benzene ring, because that would be a phenol. So R is going to change pretty much case to case. R is almost like, in algebra, everything's X, solve for X. R is generally an organic chemist X. X in chemistry usually means halogen. So if you see me write RX, I mean alkyl halide. But R will vary. Sometimes it can be H, sometimes it can't be H. Sometimes it can be literally any carbon, sometimes it can't. That sucks for you guys, right? Like those kind, if you talk to anybody learning a new language, mushy rules like that make things hard. When you start to learn a language, you like an absolute, this word always has to come second because we're a very ordered people. Okay, so R in this case is going to be an alkyl group. If I put some fluorines on this R, I can make this pKa go lower. All right. If I put really strong electron donors, I can make it go a little higher. But it's usually going to be 15 to 18. All right, 10 minutes to go. So now you're faced with, so we've got our mechanism. Go ahead and identify the acid on both sides. I'm just going to tell you, right? I've already shown it. The aldehyde is the acid. So if this is the acid, what is the base over there on the right? It's the enolate, right? So this is conjugate base. And again, I'm going to write conjugate base because that's what we do. But that just means that an enolate is a base. So all the stuff we did with Grignard reagents, you can't have an alcohol or a water around with a Grignard reagent. That's going to be true generally of enolates. That's going to make methoxide the base, and that's going to make methanol the conjugate acid. So I don't think I explicitly did this with the first acid-base reaction we did. But when trying to figure out where the equilibrium lies for an acid-base reaction, you want to either compare the two acids, the acid and the conjugate acid, or the two bases, base and the conjugate base. It makes no sense to look at the acid and the conjugate base and say which one's more stable. Like, obviously, this acid is more stable than the conjugate base. Right? The conjugate base is the same molecule. We just pulled an H off of it and made it a negative charge. It's the same molecule. you've got to compare it to something else. So we either compare the acid and the conjugate acid, so methanol versus acetaldehyde, or the base, methoxide, and the conjugate base, the enolate. Whichever one is more stable, that side of the equation is going to be favored. If you use pKa's to do this, you can figure out not only which side is favored, let me erase this too. The pKa, I'm not going to erase it, it's been there for a long time, and you guys are probably, pKa of 35 refers to that aldehyde H, not the other 3 H's. All right, if you use pKa's to figure out which side is favored, you can figure out by how much. Again, remember, pKa's are logarithmic. So if I've got a pKa of 10 on one side and a pKa of 20 on the other side, the side with the 20 is favored by 10 orders of magnitude. All right, so I've given you a pKa of 16. You can look at this structurally. So let's use the bases. Typically, when we compare the bases, we use structure, like what we know about structure, to try to figure out stability. So what do we think here? Is methoxide more or less stable than the enolate?
It would be less stable because the enolate is, yeah, the enolate is stabilized by resonance.
That is a great answer. So, gotta have other colors. All right, so the enolate is stabilized by resonance. Really important observation. Methoxide is a localized negative charge. On O. How many of you think then that she's right, that the right side is, the right side is favored? How many of you are reading into my body language and tone of voice? I could play poker with you guys at the end of the semester and just clean up. I say that, I couldn't, I'm a lousy poker player. Mask and sunglasses, do it, baby. All right, so you're wrong about which side is more stable, but your logic's right. All right, so remember when I said that ARI other thing is a guideline? It's a guideline. There are going to be notable exceptions, and the exceptions especially occur where the pKa's are close. So the way I think about it, right, this is now a delocalized negative charge, but one of the atoms we've delocalized the charge onto is a carbon, which is not particularly electronegative. Like if that atom is an oxygen and we delocalize the charge over 2 oxygens, that's way better, more stable than delocalizing over or localizing on an oxygen. But because we've delocalized onto a carbon, that sort of putting that excess charge on a carbon sort of negates the benefit we get by resonance. Turns out the pKa of acetaldehyde is like 17. There's really no way for you to answer this question, right? Like when you're within an order of magnitude, atom, resonance, induction, orbital, you kind of have to know it. But what does that also mean? If I dissolve acetaldehyde in methanol and then I add a bunch of sodium methoxide, what's going to be true about the mixture? This is a kind of sophisticated. It's going to be a mixture, but when you go closer, you're going to have, right, at equilibrium, these are close. You're going to have some acetaldehyde, you're going to have some methoxide, you're going to have some enolate, you're going to have some methanol, you're going to have kind of everything. And again, equilibrium, I haven't been through the mechanisms. I have not looked at your mechanisms yet all that closely. The equilibrium arrow means any given molecule kind of goes back and forth. right? It doesn't mean if we could label this molecule that it either gets protonated or deprotonated and it just sits there. Instead it goes back and forth. Sometimes it's protonated, sometimes it's not. Yes.
So is the enolate less stable than the?
Oh crap, yeah, so actually so you're right. The enolate is a little more stable
But,
with acetaldehyde.
but still. the
No,
left
no, it's
side
still,
is-
sorry, I'm confusing myself. This is the closest one. We're gonna do a whole bunch of carbonyls coming up. If this is a ketone, the pK is more of like 18 or 19. If it's an ester, like instead of H here, we had O ethyl or something, pK is like 23. So the left is more stable. So methoxide is ever so slightly more stable than the enolate of acetaldehyde. As we get to less and less stable enolates, that difference becomes more. But it's always within hailing distance, right? So if I put methoxide in with ethyl acetate, I can pull the acetate protons up. But again, we're going to have a mixture. All right, I'm going to draw one last reaction. And this is just to get us to draw a mechanism for that step. This is not an overall reaction. It's just the first step. Well, it's the second step of the aldol addition. Is one step, it's not two steps. So it should just be one set of arrows on the left and that gets you to the product on the right. So again, solving a mechanism, you're looking at what bonds break, what bonds form. You're going to have an arrow for all of those. If an atom doesn't, if the bonding to an atom does not change, do not have arrows going to it or from it. 20-30 more seconds. All right. So take a look at this. What bonds form? That's not so obvious, right? We have the enolate of acetaldehyde attacking acetaldehyde. So if you were to label these, let's do this. Where are 1 and 2 in the problem? Let me ask this. Is that carbon 1? Right. So at first glance, you're like, oh, carbonyl carbon, carbonyl carbon, groupie. Those have got to be the same carbons. Nope. So we did this. This is like wildly out. I do know numbers, I swear. That would be the label. I'll use orange for the arrows. So we have to make a CO pi bond. We have to lose the carbon-carbon pi bond. We have to make a carbon-carbon sigma bond, and we have to break a carbon-oxygen pi bond. So the way this would go like that. All right. See some smirks, see some laughs, see some jaws on the board. This is a lot easier if you think about the enolate as being right. I've already said this is the way the enolate will look. Like that's the dominant resonance form. If you think about the enolate being a negative carbon, which is fine, that's a resonance structure, this reaction makes a lot more sense, right? So now this is basically just O minus makes a pi bond, electrons go into carbon, and now we can just have that negative hit carbon 1. I'm going to encourage you guys to think about enolates this way. This will be my last thought for the day. Think about enolates as having a negative carbon. Most of the chemistry we're going to do is going to be described by that negative carbon doing that. I do want you to remember that enolate, the dominant resonance form, has the O minus. So we're going to pick it up there on Wednesday. If you haven't looked at chapter 21 yet, do so before Wednesday. A reminder, make sure you, well, I've handed out pieces of paper to all of you. I am going to put on Canvas whenever I get back to my office and do it. I'm going to put the synthesis supplement and the acid base online for you to download if you need it, if you're at home. Keep in mind those due dates. You can turn it in electronically. Actually, I'm going to probably say I would prefer it assigned, turned in electronically, but I wanted to give you something to do with it. That's it. I think it's not raining right now.
Realize how to do it now.
Yeah. Like your costume. Yeah, thanks.
Thank you.
Hey.
First of all, it's doing a lot better.
Oh, good.
And yeah, but
Thank you for
do
the-
still
You bet.
want
See
to
it. Thank you.
do the bonus, like the-
'Cause you bet, because you didn't. Hell, think about that.